Welcome to this problem walkthrough. In this session, we'll tackle the problem titled Maximum Students Taking Exam. Together, we'll break down the problem, analyze potential approaches, and arrive at an optimal solution. Let's dive in and explore how we can maximize the number of students in the classroom while respecting the constraints. In this problem, we are tasked with determining the maximum number of students that can be seated in a classroom, represented by a 2D array called seats. Each cell in this array indicates whether a seat is broken, represented by a hashtag, or if it is available to be occupied, represented by a dot. Students can only sit in the available seats, but there are some additional constraints to consider. A student cannot sit in a seat if there is another student directly in front of them in the same column. They also cannot sit if there is another student directly to their left in the same row. Lastly, a student cannot sit if there is another student diagonally in front of them, either to the left or the right. With these constraints in mind, our goal is to figure out how many students can be seated in such a way that none of these rules are violated. The output for this problem is a single integer, which represents the maximum number of students who can take the exam while satisfying all the seating constraints. To better understand how this works, let's look at an example. Consider this input array, seats equals, hashtag, dot, hashtag, hashtag, dot, hashtag, dot, hashtag, hashtag, dot, hashtag, dot. The output for this input is 3, which means it is possible to seat 3 students in this arrangement without breaking any of the rules. Now, let's explore how this result is derived. The optimal seating arrangement for this example looks like this: hashtag s, hashtag, hashtag, dot, hashtag, dot, hashtag, hashtag s, hashtag s. Here, we use the letter S to indicate where the students are seated. Notice that the student in row 1, column 2 does not violate any constraints, as there are no students in front, to their left, or diagonally in front. Similarly, the student in row 3, column 2 does not conflict with the student seated in row 1, column 2. Lastly, the student in row 3, column 4 is also seated without breaking any rules. This arrangement successfully places 3 students while adhering to all the constraints, which is the maximum number possible for this input. Now, let's look at another example. Here, the input is seats equals, dot, hashtag, 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 dot, hashtag, hashtag, dot, hashtag, hashtag, hashtag. The output for this case is 1. The optimal seating arrangement is s, hashtag, 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 dot, hashtag, hashtag, dot, hashtag, hashtag, hashtag. In this arrangement, only one student can sit in row 1, column 1. This is because placing additional students in this setup would violate the constraints, such as sitting directly in front, diagonally in front, or to the left of another student. Therefore, the maximum number of students for this input is just 1. In another example, consider the input seats equals, hashtag, 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 hashtag. The output here is 0. This is because all the seats in the classroom are broken, as indicated by the hashtag symbol in every cell. Since there are no available seats, no students can be seated. As a result, the maximum number of students is 0. Now, let's discuss some important constraints and edge cases that the solution must handle. First, if all seats are broken, as in the previous example, the output should be 0. Next, for single rows or columns, the solution must ensure that no 2 adjacent students violate the left or diagonal constraints. Additionally, the solution must be efficient enough to handle the maximum allowed grid size, or m equals n equals 8, meaning there are 64 total cells. Finally, in cases with sparse seating, where very few seats are available, the solution must still evaluate all possible valid seating arrangements. For example, in a scenario like seats equals, hashtag, 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 the placement of a single student must still respect all the constraints. To tackle this problem, we first need to consider the possible approaches. One straightforward idea is the brute force approach. The intuition here is to try every possible combination of student placements in the classroom while ensuring no invalid arrangements, such as 2 students being adjacent. To implement this, we generate all subsets of valid seating arrangements and check each one to determine the maximum number of students that can sit. However, this method becomes highly inefficient as the grid size increases. For an mxn grid, the time complexity is O(2)m*n, which grows exponentially and makes this approach impractical for larger inputs. Instead, we turn to a more sophisticated method, dynamic programming with bit masking. The idea here is to represent each row of seats as a bit mask, where each bit indicates whether a seat is occupied. Using dynamic programming, we calculate the maximum number of students that can be seated row by row, ensuring that no students are adjacent within a row and that no one sits directly behind or diagonally adjacent to another student in the previous row. The state is defined as dp, I, mask, which represents the maximum number of students seated in rows 0 to I given a specific seating configuration for row I. This approach allows us to systematically explore all valid arrangements while avoiding the inefficiencies of brute force. Now, let's examine how the dynamic programming with bit masking approach works. For each possible configuration, or mask, in row I, we iterate through all valid configurations from the previous row, denoted as prev_mask. If mask and prev_mask are compatible, meaning they satisfy the seating constraints, we update the state using the formula dp, I, mask, equals max, dp, I, mask, dp, I1, prev_mask, plus count, mask. Here, count, mask, calculates the number of students seated in the current row. The base case involves initializing dp, 0, mask, based on the valid configurations of the first row. In terms of complexity, the total number of states is proportional to m*2 to the power of n, where m is the number of rows and 2*n represents the possible masks for a row. For each state, we check transitions between 2*n masks, leading to an overall time complexity of m*2 to the power of n(2). This is computationally feasible for small n, such as when the number of columns is 8 or less. This approach is chosen because it is not only significantly more efficient than brute force but also aligns well with the constraints of the problem. By leveraging dynamic programming and bit masking, we can solve the problem efficiently while ensuring correctness. With these approaches in mind, let's compare their trade-offs. Starting with brute force, its main advantage is simplicity. It's conceptually easy to understand and implement. However, its exponential time complexity makes it completely infeasible for larger grids. On the other hand, dynamic programming with bit masking is highly efficient. It reduces the state space by exploiting the structure of the problem and is well suited for small grid widths due to its computational feasibility. That said, it does require careful implementation to manage the bitmask logic and ensure the transitions between states are valid. Finally, while greedy or heuristic approaches might be faster to implement, they fail to guarantee an optimal solution because they cannot account for the dependencies between rows. The key insight here is that the row-by-row dependency in this problem naturally lends itself to a dynamic programming approach. Bit masking provides an elegant way to represent seating configurations and quickly validate them against the constraints. Given the problem's constraints, particularly the small n, dynamic programming with bit masking is the most suitable method. It strikes the right balance between correctness, efficiency, and scalability, making it the ideal solution for this problem. To solve this problem, we need to think about how to arrange students in a classroom grid in a way that maximizes the number of students seated while ensuring that no two students are adjacent, whether horizontally, vertically, or diagonally. This boils down to a combinatorial optimization problem with constraints. First, let's define the problem mathematically. Imagine the classroom as a 2D grid, where each cell can either be valid for seating, represented by a 1, or blocked, represented by a 0. The goal is to identify the largest subset of valid cells that satisfy the non-adjacency constraint. A straightforward way to approach this is by brute force. We start by enumerating all possible subsets of valid cells in the grid, which involves considering all combinations of grid cells for placement. Next, we filter these subsets by checking if they meet the adjacency constraint. For each valid subset, we calculate its size and keep track of the largest one. To implement this, we can use binary representation for subsets, where each bit corresponds to a cell in the grid. Adjacency checks are performed by comparing the coordinates of the selected cells. For two cells, say, I1, J1, and I2, J2, they are adjacent if the absolute difference in their row indices is at most 1, and the same applies to their column indices. This brute force method guarantees correctness but is computationally expensive, which we'll explore further. To implement the brute force approach in practice, we use nested loops to iterate through all possible subsets of the grid and verify whether each subset satisfies the adjacency constraints. Let's now analyze the complexity of this method. First, generating all subsets of an MXN grid takes O(2)(m*n) time because there are 2(m*n) possible combinations of cells. Then, for each subset, we need to check adjacency, which involves comparing the coordinates of the selected cells. In the worst case, this takes (m times n) time per subset. Combining these, the total time complexity becomes O(2)(m*n) (m times n). While this approach guarantees correctness by evaluating every possible placement, the exponential growth makes it infeasible for larger grids. For example, even a 5x5 grid would result in over 33 million combinations. Despite this, brute force is valuable for understanding the problem and verifying results for small grids. However, for practical use cases, we need more efficient methods, such as dynamic programming or backtracking, which we'll discuss shortly. To solve the problem programmatically, we rely on specific data structures and operations. First, the grid itself is represented as a 2D matrix of size MXN, where each cell is either 1 for valid or 0 for blocked. Next, subsets of the grid are encoded as binary integers. Each bit in the binary representation corresponds to a cell in the grid, with 1 indicating that the cell is selected and 0 indicating that it's not. This compact representation allows us to efficiently generate and manipulate subsets using bitwise operations. Adjacency checks play a critical role here. We can determine whether two cells are adjacent by comparing their coordinates directly or using pre-computed adjacency lists for each cell. Now, the key operations in this algorithm include subset generation, where we use bit manipulation to enumerate all possible subsets of the grid, and validity checks, where we verify whether a subset satisfies the adjacency constraints by iterating through the selected cells and comparing their coordinates. Finally, we perform maximization by tracking the largest valid subset found during enumeration. These components form the foundation for exploring optimization techniques to improve performance. To make the algorithm more efficient, we can explore several optimization strategies. First, pruning allows us to stop evaluating subsets early if they exceed the current maximum size or violate the constraints. By eliminating unnecessary computations, we can significantly reduce the search space. Second, dynamic programming offers a structured way to solve the problem by breaking it into smaller subproblems and building up the solution iteratively. This is particularly effective when states are used to encode partial solutions. Third, greedy and heuristic methods can provide approximate solutions by prioritizing placements that maximize the number of students while adhering to constraints. These approaches can be faster but may not always guarantee the optimal solution. When implementing any of these methods, we must account for edge cases to ensure robustness. For instance, if the grid is completely blocked, the output should be 0. If the grid contains a single valid cell, the result is simply 1. For grids where all cells are valid, the optimal arrangement often resembles a checkerboard pattern to maximize spacing. These considerations help refine the algorithm and make it more adaptable to real-world scenarios. To illustrate the algorithm, let's go through an example. Suppose the input is a 3x3 grid where the cells are as follows: 111, 101, and 111. The goal is to maximize the number of students seated while ensuring no two students are adjacent. The optimal solution here involves arranging the students in a checkerboard pattern. For example, we can place students in the top left, top right, center left, center right, and bottom center cells. This ensures that no two students are adjacent, and the total number of students seated is 5. This example highlights how the adjacency constraint influences the placement strategy. Finally, let's summarize the complexity. The brute force method has a time complexity of O(2)(m*n) (m times n), which grows exponentially with the grid size. The space complexity, on the other hand, is O(m*n), as we need to store the grid in subsets during computation. While this approach is computationally expensive, understanding its mechanics provides a foundation for exploring more efficient solutions like dynamic programming or heuristics. Here, we start by defining the max students method inside the solution class. The first step is to determine the dimensions of the classroom, specifically the number of rows m and columns n. Then, we define a helper function called is_valid that checks whether a given seating arrangement for the current row, represented as a bitmask state, is valid when considering the previous row's arrangement, previous. This function ensures that no two students are seated next to each other in the same row, diagonally in adjacent rows, or directly behind one another. These conditions are checked using bitwise operations, which allow us to efficiently examine specific seat positions in the binary representation of state and previous. After defining the helper, we pre-compute all possible valid states for a row. This involves iterating through all potential bit states for the number of seats in a row, represented as 1n. For each state, we ensure that students are only placed in seats marked as available, indicated by dot in the seats grid. Valid states are collected into the valid_states list, which will be essential for our dynamic programming approach. To implement the dynamic programming solution, we initialize a 2D DP array where each row corresponds to a specific row in the classroom and each column represents a possible seating state. Initially, all values are set to -1, indicating that they are not yet computed. For the first row, we iterate through all valid states and use the is_valid helper to check if the arrangement is acceptable when there is no previous row. If valid, the number of students seated in that state, calculated using bin state.count1, is stored in the DP array. Next, we fill the DP array for subsequent rows. For each valid state in the current row, we check compatibility with all valid states in the previous row. If the previous row's state is valid and the combination satisfies the seating rules, we update the DP value for the current row and state by taking the maximum of its current value and the sum of the previous state's value and the number of students in the current state. Finally, the maximum value in the last row of the DP array gives the maximum number of students that can be seated while adhering to the constraints. Here, we start by importing the necessary classes and defining our solution class with the maxStudents method. We first determine the dimensions of the seating grid, m and n, which represent the number of rows and columns, respectively. The core of our solution involves checking valid seating arrangements, and for that, we define a helper function isValid. This function evaluates if a given seating state is valid based on the current and previous rows. For each column in the current state, we check constraints to ensure that no students are seated too close to each other. Specifically, we verify that a student seated in one column doesn't conflict with their immediate neighbors, both horizontally and diagonally. This ensures compliance with the problem's constraints on adjacency. Next, we pre-compute all possible valid states for a single row, iterating through all potential bitmask states from 0 to 2n1. Each state is validated to ensure that no student is seated in a broken seat, denoted by hashtag. If a state passes these checks, it is added to our list of valid states for later use. Once we have the valid states, we move on to initializing the DP table. This table, DP m1n, will store the maximum number of students that can be seated for each valid state at each row. Initially, all values in the DP table are set to -1, indicating uncomputed states. For the base case, which corresponds to the first row, we iterate through all valid states. If a state is valid for the first row, as determined by the isValid function with a previous state of 0, we calculate the number of students seated in that state using integer.bitCount and store it in the DP table. Next, we proceed to fill the DP table for subsequent rows. For each row, we iterate through all valid states for the current row and check if the state is compatible with the seating constraints. This includes ensuring that no student is seated in a broken seat for the current row. If the state is invalid for the current row, we skip further processing. If the current state passes the validation for the row, we then compare it with all valid states from the previous row. For each valid combination of current and previous states, if the DP value for the previous row and state is not -1 and the combination satisfies the isValid function, we calculate the maximum number of students that can be seated. This is done by taking the existing value in the DP table for the current row and state and comparing it with the sum of the DP value from the previous row and the bit count of the current state. The math.max function ensures we keep the optimal value. Finally, we compute the maximum number of students that can be seated across all valid states for the last row. This is achieved by iterating through all valid states for the last row and finding the maximum value in the DP table. The result is returned as the output of the function, representing the maximum number of students that can take the exam while adhering to the seating constraints. To solve the problem maximum students taking exam, we need to maximize the number of students seated in a classroom while ensuring no two students can cheat. Cheating occurs if students sit next to each other in the same row or diagonally in adjacent rows. The input represents the classroom as a grid where dot denotes a valid seat and hashtag denotes an empty seat. To approach this, we use dynamic programming combined with bit masking. This allows us to systematically evaluate all possible seating configurations row by row, ensuring that all constraints are satisfied. Let's begin by considering a basic example with a grid of 3 rows and 3 columns. Here, the seating arrangement alternates between valid and empty seats, forming a straightforward case to analyze. Now, we start by setting up our dynamic programming solution. First, we initialize the dimensions of the grid, 3 rows and 3 columns in this case. Then, we pre-compute all valid seating states for a row. Since there are 3 columns, there are 8 possible states, ranging from 000 to 111. However, only some of these states are valid based on the constraints. For example, in the first row, the valid state is 101, where students are seated at columns 0 and 2. States like 110 are invalid because students would be sitting next to each other. After identifying valid states, we handle the base case for the first row. For state 101, which means 2 students are seated, we set DP 0, 101 to 2, as there are 2 students in this configuration. Moving to the second row, we identify the valid state 010, where 1 student is seated at column 1. This state can transition from the first row's state 101 without violating any constraints. We then update the DP table, setting DP 1, 0, 10 to 3, which is the sum of the previous row's students and the current state's count. Next, for the third row, the valid seating state is again 101. We analyze transitions from the second row, where the valid state is 010. Transitioning from 010 to 101 is valid because it maintains the no cheating conditions. We then calculate the DP value for this state. Adding the 2 students from 101 to the 3 students already seated in the previous rows gives us a total of 5. Thus, DP 2, 101 becomes 5. At this point, the calculation for this example is complete, and the maximum number of students that can be seated without violating any rules is 5. We can see how the DP approach helps us systematically compute the optimal number of students row by row while respecting all constraints. Now, let's consider an edge case where all the seats in the grid are valid. In this edge case, every seat is valid, and the grid consists of 2 rows and 2 columns. We begin by determining all valid states for 2 columns. These states include 00, 01, 10, and 11. For the base case in the first row, state 01 represents 1 student seated at column 1, so we set DP 0, 01 to 1. Similarly, state 10 places 1 student at column 0, so DP 0, 10 is also 1. For state 11, where both columns are occupied, we set DP 0, 11 to 2. Now, transitioning to the second row, we calculate the values for valid states based on the previous row. For example, state 01 in the second row can transition from states 10 and 00 in the first row. The maximum value for this transition is 1, so adding the current states count gives us DP 1, 01 equals 2. Repeating this process for other configurations, we find the maximum number of students that can be seated in this grid is 3. Finally, let's consider another edge case where all seats in the grid are blocked. Here, the grid consists of 2 rows and 2 columns, but every seat is represented by hashtag, indicating that no students can be seated. In this scenario, there are no valid states for any row, and the DP table remains unchanged with all values set to -1. As a result, the maximum number of students that can be seated in this grid is 0. To summarize, the dynamic programming approach combined with bit masking efficiently evaluates all valid seating configurations row by row, ensuring optimal placement of students while adhering to the constraints. This method leverages compact row state representations and transition rules to systematically handle both standard and edge cases, guaranteeing the maximum number of students can be seated without violating the rules. In this problem, the time complexity arises from two main components: pre-computing valid states and filling the dynamic programming table. First, let's consider pre-computing the valid states. For each row in the seating grid, which has n columns, there are 2 to the power of n possible configurations or bit masks. For each configuration, we need to validate whether it satisfies the seating rules, such as ensuring no student is seated in a broken seat. This validation requires checking all n columns for each configuration, leading to a total time complexity of 2 to the power of n asterisk n for this step. Next, we move to filling the DP table. Here, for each of the m rows, we iterate over all valid states of the current row, which is 2 to the power of n. For each of these states, we also iterate over all valid states of the previous row, again 2 to the power of n, and check their compatibility using the is_valid function. Since this function takes n time, the total time complexity for this step becomes m times n times 4 to the power of n. Together, these steps contribute to the overall time complexity. Now, after filling the DP table, we need to extract the result. This involves iterating through all valid states for the last row to find the maximum number of students that can be seated. This step requires 2 to the power of n time, as it simply involves checking through the states. Combining all these steps, the total time complexity is 2 to the power of n times n plus m times n times 4 to the power of n. However, for large values of n, the term m times n times 4 to the power of n dominates, so the time complexity is approximately m times n times 4 to the power of n. Shifting focus to space complexity, the primary contributor is the DP table, which has dimensions m by 2 to the power of n. Here, m is the number of rows, and 2 to the power of n represents the possible states for each row. As a result, the DP table consumes m asterisk 2 to the power of n space, which is substantial for larger values of n. Additionally, we need to account for the space used to store valid states. The valid states list contains all configurations that satisfy the seating rules for a single row and has a maximum size of 2 to the power of n. Hence, the space required for storing valid states is 2 to the power of n. Beyond these, there is some auxiliary space used for temporary variables in the is_valid function, but this is negligible when compared to the space used for the DP table and valid states. Therefore, the total space complexity of the algorithm is m asterisk 2 to the power of n. This combination of space requirements ensures that the algorithm remains efficient for moderate values of n, even if it is exponential in nature. When considering the best, average, and worst-case scenarios, the asymptotic complexity remains the same. This is because the algorithm must always iterate over all possible states, 2 to the power of n, for each row, regardless of the input. Thus, the time complexity is m times n times 4 to the power of n, and the space complexity is m asterisk 2 to the power of n, across all cases. Comparing this with a brute force approach highlights the efficiency of the DP-based solution. A naive brute force method would evaluate all possible seat assignments for the entire grid, resulting in a staggering 2 n asterisk m time complexity, which is exponential in both n and m. By contrast, the DP-based approach leverages the structure of the problem to significantly reduce the computational effort. It breaks the problem into manageable row-by-row evaluations, making it exponential only in n and linear in m, which is a vast improvement. The mathematical justification for the dominant term in the time complexity lies in the need to evaluate all valid state pairs for consecutive rows. There are 4 to the power of n such pairs, and for each pair, the algorithm performs an n compatibility check. Multiplying this by the number of rows, m, gives the overall time complexity of m times n times 4 to the power of n. On the other hand, the space complexity is dominated by the DP table, which has dimensions m by 2 to the power of n, resulting in m asterisk 2 to the power of n space. In summary, the time complexity of m times n times 4 to the power of n, and the space complexity of m asterisk 2 to the power of n, reflect the algorithm's efficiency in solving the problem within the constraints. By focusing on valid states and leveraging dynamic programming, this approach avoids the pitfalls of brute force and effectively balances computational feasibility with accuracy. When tackling this problem, there are some common mistakes to watch out for. One of the most frequent pitfalls is overlooking edge cases. For instance, failing to test scenarios like empty inputs, single-element arrays, or the largest possible constraints might cause your solution to break in unexpected ways. Always ensure that your code handles both the smallest and largest inputs correctly. Another mistake involves relying on inefficient brute force solutions. While brute force is often a good starting point, these approaches tend to exceed time limits for larger test cases, so it's important to analyze the time complexity and optimize your solution step by step. Additionally, misinterpreting constraints is another source of errors. For example, assuming all elements are unique or that inputs are sorted without confirming these assumptions can lead to incorrect results. Finally, don't skip pre-processing or optimization opportunities. Techniques like sorting, using prefix sums, or leveraging hash maps can significantly reduce redundant calculations, making your solution both cleaner and faster. Another mistake to avoid is failing to validate intermediate results. For example, if your solution involves calculating subarray sums or making decisions at each step, it's crucial to double-check these outputs to ensure they align with your expectations. Overlooking this step can lead to subtle bugs that are difficult to trace later on. Now, from an interview perspective, there are a few key tips to keep in mind. First, always take the time to understand the problem scope. Clarify details such as constraints, input size, and the format of the expected output. This helps prevent misunderstandings down the line. Next, make sure to communicate your thought process clearly. Even if your initial approach is brute force, explaining your reasoning shows logical thinking, which interviewers value highly. It's also helpful to optimize incrementally. Start with a straightforward solution and iteratively refine it, explaining the trade-offs at each stage. Finally, remember that many problems share common patterns, such as sliding windows, dynamic programming, or divide and conquer. Recognizing and applying these patterns effectively can give you a significant advantage. For additional practice, there are several related problems worth exploring. These include LeetCode 46 and 47, which focus on permutations, LeetCode 77 on combinations, and LeetCode 39, which deals with combination sums. These problems often involve similar concepts and can strengthen your understanding of this topic. Now, in terms of alternative approaches, one key method is backtracking. This is especially effective for problems that require exploring all possible valid configurations. While backtracking is typically more efficient than brute force, it can still face exponential time complexity for large inputs, so it's important to use it judiciously. Another approach is dynamic programming, which is well suited for problems with overlapping subproblems. By using techniques like memoization, dynamic programming can significantly improve efficiency, though it often requires additional space to store intermediate results. Greedy algorithms are another approach to consider. These are particularly useful for optimization problems where you can make a series of local decisions to achieve a global optimum. However, greedy methods may fail for problems that require global decision-making rather than relying solely on local choices. Finally, the divide and conquer strategy can be highly effective for problems that can be broken down into independent subproblems. This method allows you to solve smaller pieces of the problem and combine their results. That said, implementation can become more complex when subproblems overlap, so careful attention is needed when applying this approach. Each of these techniques has its trade-offs, and understanding when to use them is key to solving problems efficiently and effectively. Great job completing this problem. Today, we tackled the maximum students taking exam problem, where we learned to strategically place students while respecting constraints. We discussed key takeaways, including how constraints shape our approach and the importance of balancing brute force with efficient solutions. Thanks for watching. Don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!